Hello. Okay, this is the 7th week's online lecture. So far, we have studied the electricity, but as I said, from now on, we will study magnetism for a few weeks. So the chapter in the textbook is chapter 28, and the title is Magnetic Fields. Okay, in the very last lecture, let's review that we have learned the concept of the electromotive force, which was not the force, but a kind of electric potential. Okay, and we also learned how to use Kirchhoff's junction rule and a loop rule, and there are many other rules, right? And we also learned how to understand circuit with many resistors. Try to remember how we calculated the equivalent resistor when many resistors were connected in parallel or connected in series. Okay, and we also learned how to measure the current and voltage. For current, we use the ammeter, and for voltage, we use the voltmeter. And finally, we learned how current flows in a circuit with both a resistor and a capacitor. Can you remember what happened when there was a capacitor in a circuit? When you turn on the switch or turn off the switch, the current changed as a function of time. Okay, that was the effect of the capacitor. I hope you understood them all. Okay, and in this lecture, we will finally study the definition of magnetic field. Okay, that's what we are going to study here. And we will also learn the force due to a magnetic field, which is similar to the Coulomb force due to the electric field, but there will be a difference. Okay, so let's see. And we will also learn how to use electric field and magnetic field together. And we will also learn the basic mechanisms of electric motor, meaning that how we can make an electric motor using this current and magnetic field. And we will finally learn the concept of the magnetic dipole moment. Okay, try to remember we learned the electric dipole moment previously, and let's compare that with the magnetic dipole moment that we are going to study here. So I suppose, or I hope that everybody already knows about permanent magnets, right? Is there anybody who does not know what a permanent magnet is? Okay, if so, take a look at here. These are the examples of permanent magnets. This one is called a bar magnet, and it is called a horseshoe magnet. And there are also a cube-shaped, so-called rare earth magnets. Okay, these are the examples that you can easily find from anywhere. Okay, I think you already have seen this from elementary school, right? And these permanent magnets have actually been known to humans since ancient Greece or India and China, which means that humans have been using it for a very long time. But in fact, we didn't really understand what magnets are until very recently. And then that's what we are going to study in this chapter. Okay, and let's review the basic facts about magnets that you probably already know. Everybody already knows, I assume, that the magnets have two poles, and that we call North Pole and South Pole. Okay, so take a look at the figure here. On the bar magnet, the letters are written with N meaning North Pole and S meaning South Pole. Okay, and then here is very in the small, using a small letter is written N, right? Probably this part is also a North Pole in the case of horseshoe magnet. So typically we will use the red color for the North Pole and blue color for the South Pole. Okay, and so this is actually very similar to the poles in electric charges. So North Pole, South Pole will be similar to positive and negative charges, but it's not like North Pole is similar to the positive and South Pole is similar to negative. The assignment of the signs is just arbitrary, okay? And we already know, I believe, that everybody already know that magnets have forces. So we probably from the elementary school, you had some experience of magnets pulling each other or pushing each other away, right? So as shown here, when you have south pole close to each other, these two south poles will push away each other, right? As shown by force vectors here, okay? And then exactly the same thing will happen when you have north pole close to each other. They will again repel each other, okay? And then, but in contrast, when you have a south pole and north pole close to each other, now the direction of the force will be opposite. They will try to attract each other, and then eventually they will stick to each other. Okay, I think that's what we already know. And in fact, this phenomenon is very similar to the electrostatic force or Coulomb force. So try to remember that when you had two negative charges or two positive charges, these charges will try to repel each other. And when you have one positive and the other negative charges, then they will try to attract each other. It's very similar. So there is always a similarity between the magnetism and the electricity. But there is one very, very important difference between these magnets and electric charges, which is that now in the case of magnets, you cannot separate north pole from the south pole. Try to remember in the case of electric dipole, which has both positive and negative electric charges, you could simply separate positive and negative charges only if you can supply enough force. But in the case of magnets, it is impossible because if you try to break these magnets into two, you are actually creating two separate magnets, each with one north pole and one south pole. Okay, and then if you continue to split them into smaller, then again you will keep creating always the pairs of poles. So to put it simply, it is impossible to create a monopole in magnets. Okay, I hope that's what you already have some idea. And then later we will study them in a little bit more detail, why that happens. So from the previous slide, we have seen that there is some kind of force between magnets, so that the same poles will repel each other and the opposite poles will attract each other, right? And we will study this force in a little bit more detail. And try to remember that in the case of electrostatic Coulomb force, we interpreted this Coulomb force using the electric field, right? Similarly, here we will eventually think about the magnetic version of the field. And in order to do that, let's try this simulated experiment and get some idea about this magnetic field and also magnetic force. Okay, the experiment this time is very simple. We have a bar magnet here with the north pole on the right side and the south pole on the left. And then here we have a compass. Compass is just like a small magnet, but it can easily rotate around the center. So it can visualize the magnetic force around it, okay? So the reason why we have the compass here is to visualize the magnetic force and the magnetic field around this bar magnet. Try to remember that the direction of the electric field was actually the same as the direction of the Coulomb force experienced by the positive test charge, right? So similarly, the direction of the magnetic field is same as the direction of the magnetic force experienced by this north pole. Okay, so the direction of this north pole, just like an arrow here, it will be the direction of the magnetic field around this bar magnet. So right at this position, this is pointing toward the south pole. Of course, the north pole and south pole will attract each other. And then it also shows that the direction of the magnetic field is pointing toward the south pole. So it's coming into the south pole. How about around the north pole? If I quickly move it to the opposite side, you see that it's still pointing to the right. So it's coming out. So the magnetic field around North Pole will be coming out from the North Pole. Okay. And then how about around here? So if I slowly move it, you see that this compass is no longer horizontal, but it's pointing away from the North Pole. So you can see that still the magnetic field is coming out. And then if you move further, it's still pointing away. But then over here, you see that its angle is a little bit different. So it's just like in this area, magnetic field is pointing along this direction. Okay. And then if you move further, you can see that the magnetic field here is actually pointing almost parallel to the bar magnet, but it's actually pointing opposite direction. And then slowly it's rotating further, and then you can see that the magnetic field is coming in. So therefore, you can see the magnetic field is actually coming out, and then it goes into the South Pole. Let's try that again from the bottom side. Again, okay, so again the magnetic field is coming out, and then you see that it's all again gradually rotating. Okay, and then it's coming into the South Pole. And then if you move it away from the South Pole along this direction, you see that the direction does not change, right? And you can guess that the strength of the magnetic force will, of course, naturally become smaller because you are moving far away, but the direction doesn't seem to change, right? So, in fact, okay, so this tiny compasses around this bar magnet finally shows you the direction of the magnetic field, which we have already guessed by using this compass, right? So they are coming out from the North Pole and finally goes into the South Pole. This is just like the direction of the electric field around electric dipole. Suppose you have a positive charge here and negative charge here, and this will exactly be the direction of the electric field. So the behavior of the magnetic dipole is in fact very similar to the behavior of the electric dipole, and magnetic field is also very similar to the electric field. Okay, so you have learned the electric field lines from the previous chapters. So here you can also use the same idea and then draw the magnetic field lines. Okay. So now we will study the magnetic field in a bit more detail. Here we will discuss it qualitatively first, and then later we will of course use mathematics. Okay. So the question I will ask is, what produces a magnetic field? You know, in the case of electric field, we know that electric fields are produced by electric charges, right? And then the electric field vector was written as the Coulomb force vector divided by the test charge. But then there are magnetic charges like electric charges. Of course, in the past, scientists thought about magnetic charges because that is the natural way to think about it. But there are no magnetic charges. Why? Because you cannot separate North Pole from the South Pole, just like you are separating positive charges from negative charges. Okay, so it is not the magnetic charges that produce a magnetic field, but it is in fact a flow of electric charges or a current that creates a magnetic field. Okay, so on the figure shown on the right side, so we have a straight wire. The electric current is going up, then magnetic field will be appearing around this wire, encircling to following the right hand rule. Okay, here so somebody's right hand is shown. He has his thumb pointing along the direction of the current, and then the direction of all his other four fingers will be the direction of the magnetic field, and it's going around the wire. Okay, this is how the magnetic field appears around the electric current. And if you take this wire and bend it and then make a loop like shown here, suppose now you have a loop like this so that the current is still flowing along the loop following this direction. So if you look at it from the top, it will be counterclockwise. And then again, if you understand that the magnetic field will appear around this current, take a look at this side. Here, the current is flowing in this direction. So therefore, following the rule shown above, the magnetic field will be appearing like this, going around here. Okay. And just like that, on the right side, the current is going in this direction. So therefore, again, using the same rule, the magnetic field will be going around like this. And if you repeat this around all part of the loop, you can now figure out that magnetic field will be pointing along this direction in the middle. So it's just like magnetic field comes out toward the upper direction in the middle and then go around. So it will be going around like this on the left side and going around like that on the right side, and then come back into the middle from the bottom. Okay, this is how the magnetic field will appear when you have a circular current or a loop of a current. And this is just like having a magnetic dipole or a permanent magnet in the middle with the north pole on the upper side and then the south pole on the lower side. Okay? Okay, this is how the current is related to the magnetic field. And you know, actually having a bar magnet means that there are some magnetic field already inside this material, right? So you measure magnetic field of a bar magnet without having any current. And then where does the current come from? Where does the flow of charges come from? Actually, they are electrons. So in certain elements like iron is the most famous material that show magnetism. These elements become magnetic because electrons perform some kind of circular motion inside. And in fact, this circular motion, well, in simple terms, similar to the circular motion of the Earth around the Sun or the Moon around the Earth, but that's just too simple idea. What is really going on is a lot more difficult, and you need to study quantum physics. So therefore, we will not study this in detail because it's a little bit too difficult for us. But try to remember that as a common sense, the magnetism of any bar magnet actually comes from the electrons acting like current. Okay. And then we also studied the magnetic field lines. Okay, so there is an example of magnetic field lines drawn when you have the bar magnet or magnetic dipole, the field lines coming out from the north pole and come back into the south pole. And this is just like the electric field lines when you have an electric dipole going around like that, okay, in the case of electric field. So these are actually same to each other, okay. And, okay, so now we will try to express magnetic field using mathematical equations. So before doing that, let's think about the unit of the magnetic field. So the unit of the magnetic field, we use one T, symbol T, which means the Tesla. And Tesla is, 1 Tesla is equal to 1 Newton divided by Coulomb multiplied by meter per second. And this is also equal to 1 Newton per ampere meter. It's a little bit difficult, right? But please remember that as much as you can. And it's 1 Tesla. Tesla is the SI unit of the magnetic field, and there are some other non-SI units. In fact, the unit system of magnetic field is a little bit messy, so we are not going to review them all, but only think about important units. So Tesla is the SI unit, and Gauss is not exactly SI unit, but is actually important because 1 Tesla corresponds to 10,000 Gauss. Okay, and okay,